Good. Thank you very much, Haitao, for the introduction, and thank you for inviting me to this wonderful event. It's good to be back in Loughborough. I was here once before, maybe 5 years ago, and it's great to be back here. It's going to be hard to follow Kai. I think he really raised some very important fundamental questions, which I won't attempt to address. So I think my subtitle for this is TSM, too small to matter. But that's life. I am going to refer to AI, at least in the title of the talk, as Haitao suggested. I'm presenting this, but really what I'm presenting is not my own work. It's the work of the Transit Lab at MIT. I've listed here some of the principal students and faculty. Jinhua Zhao, who many of you know, is the leader of the Mobility Initiative at MIT and also the Transit Lab, which I had founded, and I am now emeritus, and Jinhua is doing a fantastic job of leading that lab into the future. And Harris Koutsopoulos, who is a good friend and colleague at Northeastern University. Shenhao Wang is just taking up a faculty position at University of South Florida, not Central Florida, but South Florida. And the other students who are listed here. Let me also give you a little bit of my own sort of feeling about this. At MIT, and I'm sure at many other institutions that we're familiar with, there's a syndrome called the imposter syndrome. You sort of wake up at MIT and say, they made a mistake, I shouldn't be here. And I think we've all had that feeling in an institution that we belong to. And I have a little bit of that feeling being here at Loughborough, because I'm not an expert on AI. If I am an expert in anything, it's in the domain of public transport. That's really what I focus much of my professional career on. And within that context, I feel a little bit of an imposter because I'm from the US, which arguably has the world's worst public transport system. So there are multiple apologies I need to give as a preamble to this talk. Nonetheless, I will give the talk, and I look forward to a discussion of it. So what I'm going to do is talk a little bit about the Transit Lab, which, again, I've been associated with for well nigh 30 years. Talk about some of the work we did with Transport for London in terms of data analytics and sort of the evolution of that work. Talk about one example, cooperative bus holding and stop skipping, a deep reinforcement learning framework, which is, again, work that the lab folks led by Harris Koutsopoulos in this case have done, and then talk very briefly about other artificial intelligence applications in public transport. But I would group all of this in the context of what Kai said as under TSM, too small to matter. But nonetheless, I'm going to present it. Okay, the Transit Lab. One way of thinking about this is it's a cross-cultural learning experiment. We've worked extensively, as I'll talk about in a second, with London, Chicago, Boston, Washington, D.C., Hong Kong, Singapore, and also Puerto Rico, San Juan before this, which is not even listed here, but we worked with them building a metro system for about 10 years. And a lot of the idea underlying the Transit Lab is we develop methods for an agency that funds it, that's interested in it, which should be applicable more broadly around the world in very different cultural situations in different operating agencies. In Boston, let me give you an example of the dire state of public transport in the US. The Orange Line, which is the second largest subway line, second most important subway line in Boston, has closed last Friday for the next month because the infrastructure is so deteriorated that the Federal Transit Administration, the branch of the US DOT that has oversight for transit, decided it was unsafe to operate and have essentially come in as an oversight group for Boston. So I also have to apologize for coming from Boston, which has the most egregiously poorly maintained public transport system in the US. So anyway, with all those caveats. So this is an idea of the collaborations we've had. We focused on long-term collaborations with leading agencies. The MBTA Boston is an exception to leading agency, but we've had a long-term collaboration with them. And the reason for this, again, pedagogically, at a research institution like MIT, the students aren't around for that long, but the research staff and the faculty are around for that long, and it gives us as the research supervisors a chance to really get intimately familiar with the organization and the problems they're facing, the data they're using, the potential for new data, all of those things. So we had a long relationship with Transport for London that ended about a year ago now. So I'll use Transport for London as an example of this in terms of how the data analytics has evolved. We've been working with all of these agencies as they transition from, traditional manual data collection through first generation, in this case, Oyster, FareCard systems and AVL systems to phase 3 multi-sourced data analytics. The analytics go from historical to real-time to predictive. And again, this is becoming more and more interesting as we move to the right, but we started out doing a lot of historical work and then real-time applications with the feedback from the data into each one of these threads of analytics, and the applications here being again planning and policy in phase 1, control communications in real time in phase 2, and predictive decision support and service customization, information customization, and service customization in phase 3. These are an idea of the sorts of things we've been doing with Transport for London and the other organizations. One group on customer behavior and predictive analytics, did a lot of work on passenger origin destination estimation, initially based on Oyster and other sources as well, looking at reliability monitoring, predictive analytics in general, second broad category decision support and performance measurement, in terms of disruption management, bus operations under road construction, bus network design, a whole series. It's just a smattering of the work we did with Transport for London over that 15 years, and then planning and policy, which get into some of the interactions with TNCs, with automated vehicles and things like that. The general framework that we've used for doing this is having transit analytics, the heart of the brain of the system, feeding the offline functions, performance measurement, service operations and planning, feeding into the supply side, the management of the services, and the demand side, the information that you provide to customers to make good use of those services, coupled with the lower half, which is the real-time functions, which on the left feed back to the service provided through management and operations control, and the right-hand side feeds back into demand through individual customer information. So that's the overall framework we've been using. We can think of the applications as being descriptive or exploratory, control, and predictive, mapping into the 3 stages that I talked about earlier. And I'm going to give some brief examples of this. The exploratory one I'm going to talk about is with TfL using the Oyster data for unsupervised travel pattern recognition. And this gives an idea about the sorts of results that come out of this. So on the x-axis, so we're clustering customers or cards into fairly homogeneous groups and trying to understand what each group represents. So each one of these series of bars is a week's worth of travel for a row, which is a particular card or a customer, we hope, with the color coding scheme being red being the primary activity inferred between transactions, green being secondary, and the other colors being less important activities of the individual. So cluster one, we can think of as full-time employees with high income. So they're using the system 5 days a week, not at the weekends. They're far more likely to be full-time employed. The characteristics that we're mapping on the right-hand side are from the LTDS travel survey. So this is a sample of LTDS respondents provide their Oyster card number, and so we can relate for those people the demographics and the characteristics we listed here to the Oyster card, and hence the travel patterns. And then this describes the cluster one, which is sort of exclusive commuters, which have these characteristics in high car ownership, high income, and fairly young age group. This is distinct from cluster two, which is non-exclusive commuters, younger medium income workers. Again, the red is the primary activity, which is at home. The green is the secondary activity, which is at work in these cases, and the other ones are listed there by order. So this is again an example of going back to this cluster four, which I'm not going to present an example of, is school age card users who happen to have midterm vacation in the second week, so they don't travel in the second week. I mean, you could infer this other ways, but this is a very homogeneous cluster, and we can use this to identify clusters of people who might be behaving differently from the population at large, and we can tailor certain policies in terms of fares, in terms of services towards those individuals. The next example I'm going to use is Department of Energy MIT project, which is looking at transit-centric smart mobility system, which involves operations planning, control, and demand prediction, and with the linkages shown here. Again, the idea here is to develop both optimization tools and different types of AI tools to try and understand how to design transit-centric smart mobility systems. I'm going to give one example of this in the control area, cooperative bus holding and stop skipping, a deep reinforcement learning framework. So the idea here is to develop a framework to learn bus control policies based on available real-time data to reduce system-wide passenger waiting times and crowding, and particularly address the non-stationarity problem inherent in most RL-based bus control problems, because you've got multiple asynchronous decisions being made for different buses at the same time. And so the idea is to develop a framework to really more effectively make decisions, control decisions in that sort of context. So again, the idea is to recognize the asynchronicity and the dynamics associated with multiple decisions being made on different buses at different control points simultaneously, and to try and make sure that these models can be more effectively applied to the transfer to the real world. A simple example of this, again, is this: the holding problem is represented as a Markov decision process. This is a time-space diagram with the middle bus being held potentially at this point for a certain amount of time to even out the headways. So in this case, it's an agent-based simulation that's being used. I've described the formulation and the method highlights here, looking at the results, the case study was used, was applied to Route 20, a major crosstown route in Chicago in the morning rush hour. This is the route itself, with about 5 control points on the route. Again, most people are heading towards the loop, the terminus of the route. A long route, 4 to 6 minute headway. So certainly in the US context, a high frequency route. And it was an in-house bus simulator developed to evaluate the effectiveness of different control strategies. So what the results showed, and I'm not going to go into the model itself, but it evaluated in terms of headway variability, passenger wait time, reliability, buffer time, and crowding. And we looked at 4 types of strategies: no control, which is just letting the system run; even headway is a very simple heuristic to balance a gap between any 3 successive buses, to balance the headways evenly between the middle bus and the preceding and following bus. And then the reinforced learning, there were 2 models used. One just considering that each vehicle on its own, and that's the low awareness LA plot here, and the second one is the high awareness, where you're considering both the preceding headway and the following headway. So more information. And this shows what the improvement is. And what you see here, I think, is again the importance of doing some sort of control compared with no control. As you go along the route, you get bigger and bigger benefits by controlling, and in some cases some modest benefits from the more advanced reinforcement learning approach with high awareness. This shows the effects of stochasticity and runtimes, that runtimes are indeed stochastic, and we have to recognize that, and shows the range of improvement over the even headway strategy from both the low awareness and high awareness reinforcement learning approaches. And on the right, the right side shows the effect of the driver compliance. Not all drivers will do what they're told. They have their own objective function, and it's not necessarily consistent with what the agency would like to see or what the public would like to see. And so we're sort of modeling this explicitly in this approach. So I'm going to spend just a few minutes on the other applications in public transport, and then open it up for discussion. So in terms of prediction, example from that DOE framework slide that I presented is uncertainty quantification in spatiotemporal transit demand with probabilistic graph neural networks. Again, this is work that I'm reporting that I was not directly involved in. So as we talked about, travel demand during a specific time interval on an origin destination pair on a route is a random variable. And typically we don't necessarily look explicitly at the role that uncertainty plays in when we're designing the systems. And this can be quite important in any system, but particularly in public transport. So the case study on this was looking at, again, at Chicago, looking at a pre-COVID period, 2019 to 2020, an in-COVID period during the first 6 months of COVID, looking at the number of people boarding at 18 stations in downtown Chicago, aggregated at the 1 hour level, and looking at those measures of effectiveness down there. The conclusions from this, again, I'm not presenting the model, but again, the last slide has the papers that you can access to read more about any of these. So the conclusion on this, the probabilistic assumptions affecting model performance, both the mean and the prediction interval, are more important than having a deterministic architecture. And the probabilistic assumptions really are what drive the performance of the model. So that's the single most important conclusion from this. Another example, which I think has a lot of potential, is using unstructured text data for things like incident analysis. So this was work we did with Transport for London again. So many records are kept in unstructured text format, incident and controller reports, customer feedback. These are texts, they're not easily analyzed. But automated text mining can really produce good insights into what's happening and extract new information in a structured format, which is amenable to further analysis. And the example that I'm just going to refer to here is looking at incident logs on the underground network to understand what happened, how was it managed, what were the consequences, and what were the lessons learned. Again, this is very preliminary work, which I think can lead to much more significant insights into how to manage incidents in this particular case, and more generally, how to use text in a form that can really provide some insight into how to improve operations. So this is an example of that. So in terms of just wrapping up here, the Transit Lab research areas, we can think of it as sort of performance, as behavior affecting on the one side performance, on the other side decision support, and all of these elements go into the performance side, the behavior side, and the decision support side. Another way of looking at it is in terms of operations, tactical and strategic levels of input and decisions, ranging from, again, very short-run operational decisions to tactical decisions up through strategic decisions, which is where we tend to get into things that are more than just TSM. So to summarize the AI applications in public transport that our group has been involved in, we can group them into demand, both at the aggregate and individual level, mode choice, where we're looking at both TNCs and e-bikes and other things as really understanding how individuals will change their behavior. That's the first category. Second is operations control. And again, the work that we've been doing is, the example I gave was bus holding and stop skipping, looking at driver compliance uncertainty and travel time uncertainty, and also looking at train dispatching during disruptions. And the text mining example I gave. In terms of other things, Professor Abdel Ati earlier today talked extensively about computer vision. I think that's a very valuable, very promising area, along with text mining as a sort of a future initiative that we haven't done much work on yet, but I think it's a really promising area for future things. And these are some of the citations. Again, you'll note that I'm not an author on any of these because I'm reporting on work that other people did. I'm being very frank with you. But these are very good sort of supplementary, more detailed information on some of the methods that we used. And I encourage you to consult these as you will. Thank you very much.